Hi everyone, let's talk about pi donation, resonance, and its effect on carbocation stability. We can have the donation of adjacent pi electron density into the p orbital of a carbocation, and that is a stabilizing factor. Resonance stabilizes carbocations if that is a resonance donation. Okay? And essentially, that donation helps to stabilize the positive by spreading out the positive over multiple atoms. So let's take a look at these examples here. We have what we would call a secondary allylic carbocation. We're going to do a video on classifying carbocations in a bit here. But what we see is that the carbon that is positive is directly bonded to a pi system. And we could resonate electron density in this fashion to create a new contributor, which notice now is tertiary allylic. Okay? And those two carbons are sharing in the positive charge. There is a donation of pi electron density, right? The pi electron density is now going into what was the empty p orbital to form a pi bond, and the carbon on the far left is giving up density, and now it has an empty p orbital, okay? If you looked at the hybrid structure, the resonance hybrid, we would show that electron density is shared over those three carbons. Let's highlight those carbons real quick. Over these carbons, and that two of the carbons are sharing in that positive charge. When you have a positive charge on a carbon that is directly bonded to a benzene ring, we call that a benzylic carbocation, and this is specifically a primary benzylic carbocation. The thing with benzylic carbocations is there's also resonance stabilization. We can delocalize pi electron density. Remember, every atom of the benzene ring is sp2. We have a conjugated system. And we can share pi electron density into what was the empty orbital, creating a new pi bond, but we leave this orbital here empty. But of course, there's another pi bond adjacent, and we can continue to resonate this around. And I want you to maybe try this. If you drew out all the resonance structures, what you would see is a resonance hybrid that looks like this. We have the positive charge being distributed around the ring. Now, specifically, every bond is engaging in the resonance. However, not every atom of the ring would possess the partial positive in the resonance hybrid, right? So we have the delocalization of the electron density, but the positive charges only land at those carbons of the benzene ring, okay? And you could see this if you drew out the resonance structures. But the idea is, if you had a carbocation like this, okay, positive carbon here, and that's not a benzene ring, well, there's no resonance stabilization. And this primary carbocation, which is not benzylic, that primary carbocation would not be nearly as stable as this primary benzylic, which does have the resonance stabilization. And if you just looked at a secondary carbocation that was not allylic, that did not have the adjacent pi bond, that would not be as stable as this carbocation here, which has resonance stabilization of that positive charge by the pi electron donation, the resonance from the adjacent pi system. So it's very important that you think not only about sigma donation, but also pi donation. There's also sigma donation in this structure. Here's our carbocation. Here's the adjacent carbons. It's the adjacent carbon-hydrogen bonds and the carbon-carbon bonds that potentially could sigma donate into that empty orbital. So not only is there the sigma donation here, there's also the pi electron donation. And then you have this additional stability afforded to the carbocation.